Hi, I want to talk about the property of capacitive reactance when we're dealing with AC circuits. Now, if you take a capacitor and hook it up to a battery, the battery is able to almost instantly separate the charges on the plates of the capacitor, and then we're done. We've energized the capacitor, that's it. With AC, though, the capacitor can behave similar to a resistor. And here's how. If we apply Kirchhoff's law to the loop that we have a potential difference that is sinusoidally oscillating in time, and then that potential difference is a function of time minus the potential difference of our capacitor, which would be equal to the charge on our capacitor divided by capacitance is equal to 0. So at any given time, the charge on our capacitor would be equal to the capacitance times the maximum voltage times the sine of omega t plus any phase angle that we have from our power supply. Well, to find the current that we would have then on that capacitor or through that capacitor or with that capacitor, because it's not a current the way we described it. It's not charges moving through there. It just behaves a lot like a current. We'll talk about that in chapter 34 with Maxwell's equations. So the effective current of that capacitor would be the change in charge on that capacitor with respect to time. So if I take the derivative of sine omega t plus phi, I get omega times the constants that were out in front, the capacitance, times my maximum voltage, times the cosine of omega t plus phi. Now, that itself doesn't look that much like the resistance equation, because we said with resistance, our current on a resistor went like our maximum voltage divided by the resistance, and then there was the oscillating stuff after it. But what I could do is, instead of omega c times Vmax, I could write it as Vmax divided by 1 over omega c. And that looks like the same format of an equation that I have for resistance. So it behaves like resistance, it has units of ohms, just like resistance, but we call it capacitive reactance because it's how the capacitor is responding to the changing potential difference applied to that capacitor. And the capacitive reactance is equal to 1 over the natural frequency of our power supply, 2 pi times our frequency in hertz, times the capacitance of our capacitor. So if we were to take a look at voltage and current, if my voltage is behaving like the sine, my current's behaving like the cosine. So my current's doing what my voltage will be doing in a quarter of a cycle, 90 degrees or pi over 2 radians from now. So we say that current leads the voltage with capacitive reactance. And if I multiply current and voltage together, I get the sine times the cosine, which through trig identities is the sine of 2 times my angle over 2. Well, that's just a sine function, and the average of a sine function in time is 0. So the average power delivered to a capacitor is 0. As an electric field builds up, energy is being stored temporarily in that electric field, only to be given back as that electric field breaks back down. So any reactive element doesn't dissipate energy like a resistor does. So that's why we call it reactance, and that's why it's not resistance, even though they share the same unit of ohms. Thanks for watching.